chaos. The word brings certain images to mind. A messy teenager's bedroom, a traffic jam during a downpour. The stock market on a bad day, we use it to mean a lack of order, a state of randomness, a complete mess. And for most of everyday life, that definition works just fine. But in science, and especially in a field called chaos theory, the word means something else entirely. Something more specific, and something far more interesting. The central idea, the one that can be hard to wrap your head around, is this: chaos is not randomness. It's opposite of randomness. A chaotic system is a system with rules. It's a deterministic system. That means if you knew the exact starting point of everything in the system, you could, in theory, predict its entire future. There's no coin flipping, no roll of the dice, like every effect has a cause. It's a perfect chain of events, one leading to the next with absolute certainty. So, if it's not random, why does it look so messy? Why does it feel so unpredictable? That's the twist, and that's where we get to the heart of the matter. The problem isn't a lack of rules. The problem is our inability to measure the starting point perfectly. This is the famous butterfly effect. The official name is sensitive dependence on initial conditions. It's a mouthful, but the idea is simple. In a chaotic system, a tiny, immeasurably small difference in the starting conditions will lead to a massively different outcome down the road. The classic example is about weather. A butterfly flaps its wings in Brazil. This tiny stir in the air, a change so small it's practically zero, gets amplified over time. It changes the pressure slightly. That changes the wind slightly. That change gets bigger and bigger, cascading through the system, until a few weeks later it causes a tornado in Texas that wouldn't have happened otherwise. Now, is a butterfly really causing tornadoes? Probably not in such a direct way. It's a metaphor. But the principle is real. The weather is a chaotic system. To predict the weather perfectly, you would need to know the exact position, temperature, and velocity of every single particle of air on the planet. And you can't. It's impossible. If your measurement of the temperature in one spot is off by 0.0001 degrees, your weather forecast for 2 weeks from now might be completely wrong. Not a little wrong. Wildly wrong. Sunny instead of a blizzard. This is why chaos looks like randomness. We can't predict it long term. But the system itself is just following its own strict rules. It's not making things up as it goes along. It's like a game of pinball. The path of the ball is determined by physics. There's no randomness involved. The angle of the flipper, the speed of the ball, the exact point it hits a bumper. It's all cause and effect. But could you predict where the ball will be after 50 bounces? No, because a tiny change in the initial launch angle creates a completely different journey. The system is deterministic, but it's also fundamentally unpredictable in practice. This is the first step to understanding how chaos creates order. We have to redefine what we mean by chaos. It's not a mess. It's a system with hidden rules that are incredibly sensitive. It's a kind of order we just can't see at first glance. It's a pattern so complex that it looks like noise, but the pattern is there. So where is this order? If we can't predict the future of a chaotic system, how can we say it's orderly? The order isn't found in predicting the specific state of the system at a specific time. You can't predict the exact position of a leaf in a swirling river a minute from now. The order is found in the overall behavior of the system over time. The order is in the boundaries. This brings us to one of the most beautiful ideas in all of mathematics, the strange attractor. To understand a strange attractor, let's first think about a normal, non-strange attractor. Imagine a pendulum. You pull it back and let it go. It swings back and forth, but with each swing, friction and air resistance slow it down. It swings less and less high. Eventually, it comes to a complete stop, hanging straight down. That point at the very bottom, the state of rest, is an attractor. No matter where you start the pendulum swinging from, it will always end up at that one point. The system is attracted to that final state. Or think of a marble dropped into a bowl. It will roll around and around, but it will eventually settle at the bottom. The bottom of the bowl is the attractor. These are simple attractors. They're predictable points or simple loops. A planet orbiting a star follows a simple attractor in elliptical orbit. It goes around and around on the same path. Chaotic systems also have attractors, but they are different. They are strange. A strange attractor is a map of the entire future of a chaotic system. It's a shape, a pattern that the system will always follow. The system will never settle down to a single point like the pendulum. It will never repeat a perfect loop like the planet. Instead, it will wander around this shape forever, never visiting the exact same point twice, but also never leaving the shape. The most famous strange attractor is the Lorentz attractor. It was discovered by a meteorologist named Edward Lorenz, the same guy who came up with the butterfly effect. He was running a simple computer model of weather. He found that his system, which was unpredictable from moment to moment, always traced out a specific pattern when he plotted its behavior over time. The pattern looked like a butterfly's wings, or maybe a figure 8. Imagine the state of the weather is a single dot. As the weather changes, the dot moves. In Lorenz's model, this dot would move around on one wing of the butterfly for a while. It would swirl and loop, never crossing its own path, carving out a complex trajectory. Then, for no predictable reason, it would suddenly jump over to the other wing of the butterfly and start swirling around there for a while. Then it might jump back. It was constantly moving, constantly evolving, but here's the order. The dot would never leave the butterfly shape. It was confined. The system had boundaries. You could never know exactly where on the butterfly the dot would be next week, but you knew with absolute certainty that it would be somewhere on the butterfly. That shape, the Lorentz attractor, is the hidden order within the chaos of the weather system. It's a map of its destiny. It shows that the system isn't just doing anything it wants. It's following a deep underlying structure. It has freedom, but only within a very specific set of constraints. Think of it like a person pacing in a house. You don't know if they will be in the kitchen or the living room in 5 minutes. Their path is unpredictable, but you know they won't suddenly be in the house next door. The walls of the house are the attractor. A strange attractor is just a house with a much more intricate and beautiful floor plan. A plan that the system itself creates and follows. So this is the second bigger step. Chaos creates order by confining a system to a specific, complex, and often beautiful pattern called a strange attractor. The system is unpredictable in its details, but its overall shape and behavior are perfectly defined. The order is not in the point, but in the picture. There's another layer to this. The geometry of these strange attractors is not the simple geometry of squares and circles we learned in school. It's a different kind of geometry. It's a geometry of nature. It's called fractal geometry. A fractal is a shape that exhibits self-similarity. That means if you zoom in on a piece of the shape, you see a smaller version of the whole shape. And if you zoom in on a piece of that smaller version, you see an even smaller version. This pattern repeats forever, at every scale. Nature is full of fractals. Think of a coastline on a map. From a satellite, it looks jagged and complex. If you zoom in on 100 miles of it, that section also looks jagged and complex. If you walk along 1 mile of it, it's still jagged and complex. The pattern of bays and peninsulas looks similar at every scale. A tree is a fractal. A large trunk splits into smaller branches, which split into smaller branches, which split into twigs. The pattern of branching is similar at each level. A fern is a perfect example. Each frond is a miniature version of the whole fern. A lightning bolt, a snowflake, a river delta, the blood vessels in your lungs. They are all fractals. Strange attractors are fractals. That intricate, infinitely detailed shape of the Lorentz attractor has this property of self-similarity. If you could zoom in on one of the lines it traces, you would find that it's not a single line at all, but a collection of more lines, which are themselves collections of more lines. This infinite detail is why the system can wander around forever without ever repeating the exact same path. There's always more space to explore within the pattern. What does this tell us? It tells us that the complexity we see in a chaotic system isn't just random noise. It's a very specific kind of complexity. It's generated by a simple rule repeated over and over again. The process of making a fractal is often incredibly simple. You start with a line, and you apply a rule for every line, replace it with this other jagged shape. Then you do it again to the new shape. And again. And again. From a very simple starting point and a very simple rule, you can generate a shape of infinite complexity and beauty. This is a profound idea. It means that the chaotic, unpredictable world around us might be governed by surprisingly simple rules. The complexity isn't in the rules themselves. The complexity emerges from the repeated application of those rules. The order, the fractal pattern of the strange attractor is the direct result of a simple deterministic process. It's creation, not confusion. It's a system building its own intricate structure from the ground up. So, chaos theory gives us a new lens to look at the world, and when we use it, we start to see this principle of order from chaos everywhere. It's not just in abstract computer models, it's in the real world. Let's look at biology. Your heartbeat, for example. You might think a healthy heart beats like a metronome, perfectly regular, but it doesn't. A healthy heart has a slight chaotic variability in the time between beats. When doctors plot this variability, it traces out a strange attractor. This chaos allows the heart to be flexible, to adapt instantly to changing demands like standing up or running for a bus. A heart that becomes too regular, too predictable, is often a sign of disease or old age. It has lost its chaotic adaptability. In this case, chaos is health. The order of the strange attractor is the pattern of a functioning responsive system. Too much simple order is a sign of trouble. Or think about animal populations. The number of fish in a lake from year to year can seem to fluctuate wildly. Ecologists have models, like the logistic map, that are famously chaotic. With a certain birth rate, the fish population will be stable. Increase the rate a little, and the population will oscillate between two numbers, a big year and a small year. Increase it more, and it splits into 4 numbers, and then 8, and then suddenly it becomes fully chaotic. The population from year to year looks random, but it's not. It's following a deterministic rule. And if you plot its behavior, you see it's confined to a specific pattern, an attractor. The chaos prevents the population from either dying out completely or growing so large that it destroys its environment. It's a mechanism for long-term stability through short-term unpredictability. This pattern appears in human systems too. Look at the stock market. It's famously unpredictable, but it's not completely random. If it were random, a stock could be worth $1 one day and $1 million the next. It doesn't do that. It moves within certain bounds. It has trends. It responds to news and fear and greed. These are the rules of the system. Its behavior is chaotic. It's highly sensitive to initial conditions. A single tweet from an influential person can send ripples through the entire market, a perfect example of the butterfly effect. But over time, the market's behavior is constrained. It operates within a larger economic system that provides boundaries. Its wild swings and unpredictable jiggles are the movement of a system along its own strange attractor. Even something as simple as water flowing from a faucet shows this transition. Turn it on just a little and you get a smooth, clear stream. This is called laminar flow. It's predictable and orderly. Open the tap more and the stream starts to waver. And then suddenly it becomes turbulent. It's a mess of splashes and eddies. That is chaos. But it's not random. The motion of every water molecule is governed by the laws of fluid dynamics. Within that turbulence, there are temporary swirling structures called eddies, which form and dissolve. There is a hidden dynamic order to the flow. The system has found a new, more complex way to organize itself. This leads us to a final, crucial idea. The place where things get really interesting is not in pure order or pure chaos. It's on the border between them. This is sometimes called the edge of chaos. Think of 3 states a system can be in. The first is a state of rigid order. Think of a crystal. Every atom is locked in place. It's stable, it's predictable, but it's also dead. It can't adapt, it can't change. It can't do anything new. The second is a state of total randomness, or true chaos in the everyday sense. Think of the molecules in a gas bouncing around with no structure at all. The system has no memory. It can't hold any complex patterns, it's just noise. The third state is the edge of chaos. It's the transition zone between the crystal and the gas. A system at the edge of chaos has enough stability to maintain its structure, to have a memory. But it also has enough instability, enough chaos to be flexible, to adapt, to evolve, and to create new patterns. Life itself exists at the edge of chaos. A living cell is not a rigid crystal, but it's also not a random bag of chemicals. It's a highly structured, complex system that is constantly changing, adapting to its environment, and reacting in unpredictable ways. The brain is another perfect example. Your thoughts are not perfectly ordered and predictable. If they were, you could never have a new idea. But they aren't completely random noise either. They are a stream of connected, structured, yet creative and unpredictable patterns. The brain operates at the edge of chaos. This is perhaps the ultimate way that chaos creates order. It provides the mechanism for complex systems to emerge and thrive. The chaotic dynamics allow for exploration and creativity. The pull of the attractor provides the stability and structure. By constantly pushing and pulling between these two states, a system can achieve a level of complex, adaptive order that would be impossible in a purely stable or purely random world. So, how does chaos theory create order? It reframes the question. It shows us that what we call chaos is already a form of order. A deep, complex, and generative order. First, it's based on deterministic rules, not randomness. The unpredictability comes from our limitations, not from the system's lack of structure. Second, it reveals a hidden order in the form of strange attractors. These are the bounded shapes that constrain the behavior of a chaotic system, proving it is not just flying off in any direction. The order is in the whole, not the parts. Third, it uses the simple repeating logic of fractals to generate infinite complexity from simple rules. This shows how nature builds its intricate patterns, from coastlines to cauliflowers. The order is in the process of creation itself. And finally, it suggests that the most dynamic and creative forms of order in our universe, like life and intelligence, exist at the edge of chaos. They harness the unpredictable dance of chaos to adapt and evolve, creating ever more complex structures. Chaos is not the breakdown of order. It's not the enemy of structure. It's a different kind of order. It's the engine of change. It's the force that prevents the universe from becoming a static, frozen crystal. It's the messy, unpredictable, and beautiful process that allows simple rules to blossom into the infinite complexity we see all around us. It's the pattern beneath the noise, the system behind the madness. It's the universe's way of being creative.